A video camera feeds images to a television monitor. It dissects the field of view into an electronic signal. The monitor then reconverts this back into an image on its screen. When the camera points toward the monitor's screen, images are fed back into the camera and circulate around this closed loop. In the following video feedback experiments, an analog image processor is connected in the electronic portion of the feedback loop. It consists of modules to add, multiply, and synchronize images. In its programming and parallel operation, the system is very similar in architecture to a conventional analog computer, except that it simulates spatially extended dynamical systems. The camera is mounted to rotate on its optical axis. This is centered on the monitor's screen. Zooming in, as unity spatial magnification is reached, dynamic patterns spontaneously emerge. During one circuit of the feedback loop, an image is manipulated by various optical and electronic transformations. Their composite effect during one video frame time determines the overall dynamics. Dynamical systems theory pictures the behavior of any system as the motion of a point in a space of states. In video feedback, a state is a single image. The temporal evolution of patterns is represented then by a trajectory moving through the state space. Energy flows through the video feedback system and is dissipated. This process is analogous to friction in a mechanical oscillator. Dissipation causes an initial pattern to evolve through a transient phase into a small region of the state space, called the attractor. Attractors fall into a hierarchy of distinct behavioral classes based on their complexity. Fixed points and limit cycles describe regular, repetitive dynamics, whereas chaotic attractors describe unpredictable behavior. A fixed point corresponds to the conventional notion of equilibrium, a single static pattern toward which nearby initial patterns tend. These nearby patterns are said to be in the fixed point's basin of attraction. After perturbing a system away from its attractor, the trajectory returns. Here, the reddish light in the lower left comes from a flashlight that distorts the pattern, attempting to drive the system away from its attractor. But once removed, the original fixed point cross pattern returns. A pattern can be so distorted that the resultant image is closer to and lies in the basin of another attractor. A limit cycle attractor describes periodic behavior. In the state space, a sequence of patterns is visited repetitively. This sequence, for example, repeated exactly as shown for several hours, and when perturbed, returned to the cycle after a short transient. The following 6 examples illustrate some of the more complex video feedback dynamics. The interdigitated light and dark fingers of video dislocations are reminiscent of the convection cell patterns found in fluid flows. Similar patterns occur in viscous fingering in ferrofluids, domains in thin two-dimensional magnets, flux patterns in type 2 superconductors, and the ocular dominance patterns in the visual cortex. The mechanism at work here is called lateral inhibition, where light in one area inhibits light in neighboring regions. A natural consequence of rotation and magnification is the appearance of logarithmic spirals. This sequence illustrates two-dimensional crystal-like patterns of dots. At several times as the system relaxes, the dots align themselves along logarithmic spirals in a pattern identical to that found in sunflower phyllotaxis. With large spatial magnification and light gain, the video dynamics becomes very sensitive to small, uncontrolled fluctuations. If a fluctuation of sufficient size occurs, it becomes amplified to macroscopic, observable behavior. In this sequence, note that although the bursting behavior appears quite random, there are only several characteristic amplification pathways. For example, a grain texture pattern and a sequence of growing balls. In this sequence, fluctuations at the top are amplified as they move down the screen, giving a fluidity and capriciousness typical of a stream or waterfall. In contrast to spirals, pinwheels have straight radial boundaries that rotate about the center. Here, on each pass through the feedback loop, the patterns are rotated and the three colors are cyclically mapped into each other. This is a simpler example where a dark region maps into a light region, and a light into dark. The camera is also rotated 90 degrees, giving an overall fourfold symmetry. Intermediate between logarithmic spirals and pinwheels are spiral waves reminiscent of the spatial patterns found in oscillating chemical reactions. The video system in this regime is an active medium, every point of which has a well-defined and synchronized oscillation, except for the phase singularity at the center. The next three sequences examine the effect of a slow change in a parameter on the dynamics. To isolate the effect of camera angle on the overall symmetry of the patterns, in this sequence the camera is very slowly rotated through approximately 5 degrees. Additionally, a mask has been placed over the monitor to impose annular boundary conditions. The pattern symmetries lock and unlock as the camera passes through simple rational angles. Fixing the camera at an angle where a fourfold and a higher symmetry coexist but are marginally stable, chaotic sequences of patterns sporadically transit between the symmetries, their competition driving the unpredictability. The second bifurcation example illustrates the appearance of a stationary pinwheel pattern. The control parameter here is the light gain, that is the amount of light amplification during one pass around the feedback loop. This is varied simply by increasing the camera's f-stop. Initially, diffuse boundaries appear between the light and dark regions. At higher light gain, they become quite distinct boundaries. A cubic nonlinear element is connected in the electronic portion of the feedback loop. Each picture element's intensity is operated on with a cubic one-dimensional map. Continuing as in the previous sequence, the light gain is increased and the system visits more and more of the electronic processing's nonlinearity. The simple static pattern gives way to finer spatial structure and time-dependent dynamics. Eventually, the behavior becomes quite complex when spatial coherence is lost, then analog of the transition to fully developed turbulence. Chaotic attractors are the forms underlying unpredictability. By animating a sequence of cross-sections through these objects, we shall explore the geometric structures responsible for chaos in 5 different three-dimensional attractors. In the 1920s, a Dutch radio engineer, Balthasar van der Pol, invented this dynamical system as a source of stable oscillations for radio wave transmitters. He also studied it as a model for the heart's stable beating. From this work, van der Pol published in 1927 the first experimental report of noisy behavior arising in a simple, nonlinear system. The oscillator's position will be plotted horizontally, its velocity vertically. As the driving force repeats periodically, it is said to be at a particular phase of its oscillation when it is a certain distance through a cycle. A cross-section, or Poincaré section, is built up by placing a dot at the oscillator's current position and velocity each time the driving force passes through a given phase, such as going through 0 positively. For each cross-section here, the points are accumulated from 2,000 oscillator cycles. The variation in dot density on the attractor's cross-section indicates that orbits are more or less likely to visit different regions. As the cross-section plane is moved through the attractor, the geometry of stretching and folding becomes clear. The attractor seems to be a wrinkled tube. After the cross-section has been moved forward in time by one driving cycle, the attractor structure repeats. Its overall shape is that of a torus or donut. Moving around the torus corresponds to varying the driving phase. Stretching occurs largely at the attractor's top and bottom. Folding nucleates at the left and right sides, where the lines are pulled out and pinched, then stretched and folded down onto the attractor. As if kneading dough, this process shuffles orbits on the attractor. In each section, there are 3 different foldings occurring, each in a different stage of completion. Following a fold from nucleation, it takes only 1.5 cycles until the fold is flattened onto the attractor's body and is no longer discernible. Here, the speed of moving the cross-section through the attractor increases. The equations of motion specify a vector field through which orbits flow in the three-dimensional state space. Symmetries in the equations appear in the vector field, and so the attractor conforms to these. 2 cross-sections are superposed. One is held stationary for reference, the other is moved through the attractor. Stopping halfway through the driving cycle illustrates a rotation symmetry. The 2 sections are identical, except that they are rotated 180 degrees about the origin. This symmetry derives from that of the sinusoidal driving, the second half of which is an inversion of the first half. Continuing on through the cycle, the sections again coincide after one driving period. Reducing the driving amplitude and frequency slightly from the previous settings leads to a period doubling bifurcation sequence. This attractor consists of 2 bands in the cross-section, or, in the full 3-dimensional state space, a ribbon looped back onto itself. This attractor describes an overall period 2 oscillation with chaotically modulated amplitude. The orbits repetitively visit one band, then the other, while within each band the motion is chaotic. For the system to exhibit period doubling behavior, the original left-right symmetry of the equations must be broken for the attractor. Here, folding occurs on the right side only. There is, however, another mirror-symmetric attractor nearby that folds on the left side. Taken together, the 2 attractors conform to the required overall symmetry. The largest amount of stretching again occurs at the attractor's top and bottom. But as this is compensated by contraction along the same directions, it does not shuffle or fold orbits on the attractor, and so contributes nothing to the deterministic unpredictability. Only the relatively small folding on the right is responsible for the chaos. Nonetheless, external noise is temporarily amplified by the laminar stretching, and so may add significantly to the appearance of unpredictable behavior. Changing the parameters again reveals one example of the very complex attractors common in the van der Pol oscillator. The dots inside indicate some of the attractor's fractal structure. Zooming in on this portion reveals lines within lines. This structure on finer length scales is a result of the stretching and folding process. The folding process here is much more pronounced. There is an overall period 3 component to the noisy behavior, corresponding to each of the 3 folding regions being very probable. One feature not shown is the coexistence of a stable period 1 orbit inside the central triangular region. At slightly higher driving amplitude, the boundary between these two attractors collides with the circumscribing chaotic attractor. It is annihilated, leaving only the period 1 orbit. Duffing, a German mathematician, studied this oscillator at the turn of this century. Physically, it describes the motion of a ball rolling with friction in a nonlinear bowl. The bowl has steep sides and a hump in the middle separating 2 wells. The driving corresponds to moving the bowl up and down periodically. The attractor appears thick, revealing some of the many fractal layers. The contraction onto the attractor due to friction is much less than in the previous examples, which appeared as lines in the cross-section. As the section moves through the attractor, the effect of the steep walls and unstable hump in the middle can be seen. The walls contain the attractor, reflecting and folding it back toward the center, and the hump causes a large amount of stretching at the center. As a physical system, the driven pendulum was used to regulate clock movements in early mechanical timepieces. Today it is used to model many physical systems, such as superconducting Josephson junctions, ion motion in crystals, and elementary particle accelerators. The driven pendulum is similar to the Duffing oscillator, except that the nonlinear bowl has no confining walls, and is instead a washboard over which the ball rolls. The driving again corresponds to vertical periodic motion of the washboard. The potential well is periodic in the horizontal coordinate of oscillator position. The attractor exhibits this spatially periodic symmetry. A 5-well portion of the infinitely long attractor is shown. The local structure is similar to that of the Duffing attractor. It appears thick, and the folding and stretching is largely governed by the negatively curved humps in the nonlinear potential well. There are 2 time scales in the pendulum's chaotic behavior. A short time during which the oscillator stays localized within a few wells, and a long time over which the attractor diffuses in position. This diffusion is manifested in the cross-sections as the spilling over of the attractor from one well to the next on each cycle.